Hi, my name is Jim, and today's topic has to do with op amps that have dual supplies and single supplies, and then we're also going to be talking about rail-to-rail op amps, which are relatively new on the scene. They're designed with CMOS transistors instead of bipolar transistors. So let's begin our discussion with a typical circuit here, kind of drawn in a mess, but what we're seeing here is a dual supply operational amplifier. It's the way we see in labs, which is very convenient for lab work. And the op amp itself has a negative supply terminal and a positive supply terminal, and the grounds are independent of the operational amplifier, meaning that there is no ground terminal connection to the op amp. Basically, if it's biased up properly, it floats between plus and minus 15 volts, and these ground references here will provide an output which is approximately 0 volts, with all due respect to input offset currents and delta base current anomalies caused by different impedance paths to ground, and VIO and other voltage at the output caused by slight variations in the process of the input and so forth. So we're going to bypass that and just say basically that the output in this particular circuit is going to be 0 ground. Now the problem we have here is that we have a load resistor, and we really don't know what that is. This could be an op amp that's actually providing some power, for example the vintage LM380, and it's going to be shoveling buckets full of current in and out of the load resistor. It's going to be supplying current from VCC into the load resistor and sinking current from ground into the negative supply. Now basically what that means is that we're going to be having ground currents, significant ground currents possibly, flowing in RL, our load resistor, but what we do not have is any of these ground currents flowing on the input circuit if these are returned to the ground on the power supply filter. Now this is called a star ground, and these grounds all come back to this point. Any change here means that everything floats up and down at the same time, and there's no differential voltage, and hence any noise or ability to oscillate in the circuit is highly suppressed. Now, as we're going to see coming up here in the next diagram, where we have an operational amplifier with a single supply rail, as such is not the case. So the good news about this is that the ground is not used by the actual operational amplifier for any current draw. To say operational current, we have to be careful with the return path from the load resistor, and what that tends to do is to make for a relatively clean output. Now notice that our main supply filter here is plus and minus. I have a couple of electrolytics in series here. Plus, it should be 15 volts, all fixed, 0 volts and negative 15 volts, with the grounds connecting into the common ground of the filter caps. And when I say that, I mean common ground. In some of our equipment we have a common ground pad which is about that big around, with various PC traces leaving it to avoid any anomalous noises interject, because as we will see, circuit board traces are very, very bad conductors. Now, looking at a single supply, and what the advantage of this is that, well, you don't need all the components associated with a negative supply, is we can get things to work just fine. The only issue is that now our negative lead of our operational amplifier is following the common ground path. Now if we expect to get a equal swing in a positive and negative direction with a sinusoid input, is what we have to do is provide a false ground here, which is called a pseudo ground. Now the false ground is typically VCC divided by 2, or 7.5 volts. So it's provided typically by a couple of resistors in series. I've chosen 10Ks here. that may or may not be appropriate depending upon the impedance of these resistance of these other parts. But the problem we end up with here is that now we're sourcing current into our load and we're sinking current from ground. Well, I should have a cap here, which I just did, put one there. Sinking current into ground, and this current flow through this circuit trace is going to affect other circuits. And notice I said possibly, in fact, will affect. There's no question about it. So this ground would be returning to the main filter capacitor, and if we compare a single supply circuit with a dual supply circuit very quickly, we can notice some interesting outcomes. First of all, the dual supply circuit has a good power supply rejection ratio, and that's referred to as PSRR. Now what that means is that if the 15 volts plus or minus bounces, say due to changes in current flow here, and this is PC traces, so these are impedance, it'll be suppressed by a relatively large number. I'm going to throw out 70 dB, some are better than that. So that's a good thing, is that the noise on the positive and negative supply lines are suppressed from appearing in V out, power supply rejection ratio. The supply current does not use ground. That's helpful because of the drop in the ground trace caused by the supply. And in our example here, our maximum output voltage is approximately 30 volts, plus or minus 15, minus the saturation voltage on the positive and negative side. And I've allowed VCE, it's collector to emitter, or VSAT rather, SAT, saturation, to be 2 volts. So we get approximately maybe 26 volts peak to peak. That depends on a lot of things, like the frequency of the signal is very important, because if the frequency is too high, we're going to get into slew rate limiting, which will definitely not allow us to hit 26 volts peak to peak. The downside of this is it needs 2 supplies, and you probably haven't seen much other than your computer that you plug in. It's a multiple supply, and all that's handled inside the power supply module. Now, comparing that to the operational amplifier circuit that's single supply, and second power line here is connected to ground, and again, we have pseudo grounds that bias a transistor at 15 volts divided by 2, is what we see here is the supply current does involve ground. In other words, it's flowing through ground here, and these are going to other circuits, and seeing that we have impedances here, which I'll explain on the next page, is going to cause noise. The other circuits are digital, perhaps not so much. If they're high gain preamplifier types, it's a big deal. So the voltage peak to peak in this case would be 15 volts minus 2 times the saturation voltage, which would be approximately 11 volts peak to peak. So what you can see is that the output of a single supply with a single 15 volt source is significantly reduced. Now what we can do with, say, a 741 is to run this up to 30 volts, and that would give us approximately the same peak to peak output voltage. The power supply rejection ratio, which again is the ability for noise on the supply pins to be suppressed in the output, can be severely compromised by this. So we have to take into account some features to offset the nicety of not having to provide a negative supply voltage. Need for one power supply, that's a very positive thing. And what we end up with in a good circuit board design is more complex ground wiring. So let's take another look at the details of this. Here we have a single supply operational amplifier circuit, and I mistakenly connected this to ground, so that's crossed out. It goes to the pseudo ground, which in this case would be approximately 7.5 volts again. bias resistor for the non-inverting input also goes to pseudo ground again, so the output can be basically VCC over 2. And then once again we would have a capacitor here to isolate the load, and the polarity would be such, it would be an electrolytic if, say, this is a power amplifier and we're punching a speaker here with a 4 or 8 ohm impedance. So it would block that, and what this essentially does is it makes the signal going to the speaker, in this case, if you will, an AC signal centered on ground. Because remember that the impedance of a capacitor, X sub C, goes to infinity as F goes to 0, and DC is considered to be 0 frequency. Anyway, if I take my little ground here and put little circle points in it and replace it by a typical ground trace, is what I've got is Z1, which is a series L and a series with R. Z2, same deal. Z3, same deal. Z4, same deal. And if I want to kind of combine things and see what's going on at these 4 points in the circuit, and I'm ignoring complex impedance here, I just want to make the point, is what we have is the voltage bounce at VA is the current that's flowing in this, which would be in this direction I, times the impedance here, this is my current flow, times the impedance Z1. So basically point A is going to be kind of bouncing up and down depending upon the current flow in it. Likewise, the voltage at VB now is the current flow plus the sum, again, without getting into complex numbers, of Z1 and Z2. DC, worse yet, I times the sum of the 3 impedances. And finally, the V at point D, which would be the current flow times the sum of all of these impedances. So it's very easy for us to end up with a ground which is not 0 volts. And that almost always is bad. So what this can cause is noise. You can imagine if there's other components in the circuit that are contributing to I here, and since we're biased at this point, that's just going to feed right into our operational amplifier and be added to the signal. The second thing is, if it's really bad, is we can end up with oscillations. And it doesn't take much to do that with certain integrated circuits. You know, ground traces have to not only be laid out correctly, but have to be thick. And you can order boards with 1/2 ounce to 4 ounces of copper, and that would be the weight per square foot of the board. The more copper, the lower the impedance for a given trace width. So circuit boards are very terrible, and what I've not shown in here are any of the capacitive effects that would occur between traces. And further, there's another component called dielectric absorption, which means that the trace itself has capacity to another conductor, and if that capacity, capacitor, it's parasitic, is discharged after a period of time, the charge reoccurs. It's a nasty phenomenon, dielectric absorption. So the solutions on this is possibly a ground plane, and that basically means that if you have a circuit board, it may end up being 4-layer, and one complete layer of that is nothing to ground. There's no traces on it. And the other layer would probably be for the supply voltage. And it's kind of strange because as the current flows in a ground plane circuit board, the return current is exactly over the top of it. So you have to be careful not to have anything that interrupts that, or the impedance of the ground path goes up. And that's the nature of the magnetic fields canceling each other and producing in solid copper, whether this or not, a lower impedance for the current flow. So what's really bad is if you have mixed analog and digital and you kind of don't pay attention to the grounds. Now what I've done here is kind of the worst case, is I have an analog system here and a digital system here, and when digital circuits switch, there's typically a very small point in time when this output transistors, the ones that turn the output high and the ones that make the output low, are momentarily turned on at the same time, and what that does is it produces a through current, which manifests itself as a relatively fast spike of current, which is seen here and here. Now, on our ground trace, as you can probably guess, is that this spike is going to be interfering with or providing a signal into the input of this here that can be amplified. Now, this is so critical that some complicated digital logic circuits, for example, A to D converters, preamplifier, complicated preamplifier integrated circuits, have two grounds, one for the analog and the other for the digital. So if you want to keep a really clean supply, you have to kind of take into account those two grounds and run those independently back to your main filter cap. So if it's critical enough for a manufacturer to supply two grounds, do understand that it's an important concept. So we have ground bounce. Basically what we have is bad ground wiring on the part of the circuit board designer. Has to take that into account, and because you design a board and everything's electrically connected together, doesn't mean the board is a good board. If we take a look at the dual supply here, is what we're going to see from the standpoint of output swing again, and I just want to detail this before I move on, is that we have supplies of plus and minus 15 volts, and in blue here I've drawn the saturation voltage loss, which approximately 2 volts. So our peak-to-peak swing on this is approximately 26 volts, with all due respect to slew rate limiting. In a single supply, we have 15 volts, and again I've shown the saturation voltage sitting off ground by 2 volts and down from the 15 volt supply by 2 volts, and that gives us an output swing of 9 volts peak to peak. So if you want to have the same output swing, as I mentioned before, your supply voltage would have to be basically twice what it is. So the advantages of a single supply are quite obvious, is you don't need to have a center tap transformer or whatever, and the disadvantages are is you have to give attention to what that supply can produce in the output. Now, it's true that you can have a switch mode power supply which will take 15 and very quickly and easily make it 30 volts, but that's adding parts to the circuit. Power supply rejection ratio, PSSR, is obviously a big deal because it's specified by the manufacturers. It's specified as a positive number in decibels, but it's like ripple rejection ratio. It means that any noise on this is going to be suppressed. So that's actually, in the mathematical context, treated as a negative decibel value. So what I've shown here is a bipolar supply, not device, I'm talking about two supplies, and realistically our 15 volts should be flat because the internal impedance of a DC source is 0 ohms, meaning that there can be no other voltage on that point except 15. However, we're connecting this by circuit traces or wire, and we have some bounce that's riding on top of it due to other circuit switching and whatever, possibly coming in from the power lines into the power supply. And we have the same thing down here on the negative supply. So PSRR is the ability to inhibit these changes from appearing in the output. And this is given again as a positive number, but if you wanted to find the actual voltage at the output that associates with a given peak-to-peak here, your equation would be, say, negative 70 dB equals 20 log of. So the words power supply rejection ratio means that the quantity is negative. So in a common ground here, if we take a look at this, we have worse problems having to do with the power supply rejection ratio. And kind of remember in the United Kingdom, in a recording studio, the absolute worst case signal to noise ratio after all processing sits around 67 dB, meaning that the noise components have to be 67 dB beneath signal. Now that may seem like it's not too much, but when you start out, you have to pay deep attention to every single detail to meet that relatively mundane 67 dB specification. And some stages will be over 100 dB. It'll be good, but the problem is you add things together and this noise becomes additive and can subtract from the overall goodness, quality of your signal. So if we look at this from the standpoint of generating our pseudo supply, which is 7.5 volts, the way it's usually done is with a resistive voltage supply with these two values being equal, so you're able to swing in the positive and negative direction the same. And if we take a look at this, and it's a 50% voltage divider as we see, and now I'm going to say that I have a V bounce here, and what I want to do is find out how much that's going to be at the pseudo ground. Now the IC itself is rated quite high at 70, maybe 80, maybe 90 dB of rejection, but when we use the pseudo ground here, is what we end up doing is basically taking the bounce and dividing it by 2. So eliminating the bounce as a number is what we end up with is the voltage bounce at the pseudo ground is 20 times the log of 0.5, and that very nice rating of the operational amplifier itself is completely wrecked by the circuit and comes in here as a 6 dB power supply rejection ratio parameter of the circuit. So that's horrible. How are we going to fix that? Basically put, if this guy changes by 0.5 volts, what's going to happen here is this is going to bounce by 0.25 volts. So a solution to this is to bypass it, and we can put a relatively large electrolytic at the junction from the positive power supply to the pseudo ground, say 15 volts, and this would be 7.5 volts. And what this would tend to do would be hold the voltage across our constant as this guy floats up and down. So what that means is sometimes the voltage provided to the pseudo ground is coming from the supply and ground, and sometimes it's being sourced and sunk by the capacitor. So what we have to do is to size this such that the lowest component of the bounce is effectively bypassed. And when you do that, if we're interested in looking at the time constant, is what we have to remember is since the internal impedance of a voltage source is 0 volts, from the standpoint of an AC signal, these two resistors are in parallel. So what that would look like would be if we drew a line from here over to ground, and you can kind of see that R and R, whatever values they be, are in parallel. And then from that we can get an idea of the time constant which associates with the lowest frequency of the bounce that we expect. Now the bad side of this is we have a pole here, which means that it does not eliminate changes down to very low frequencies. And also it adds a part, and in addition to that, there's a startup issue here. The circuit can't operate properly until this reaches the correct pseudo ground voltage. And this cap, say initially is starting out at 0, has to charge up at 7.5 volts. So the time constant on that again is the 2 R's in parallel. Okay, everything's low voltage today. We have our cell phones and MP3 players and so forth, and well, how do we do that? And if we're operating from a single lithium-ion rechargeable cell, and there are lithium-ion non-rechargeable cells that sit in around 1.5 volts, well, this is a rechargeable variety, sit at 4.2 volts, so plus or minus 50 millivolts when they're fully charged, and at discharge, the fully discharged lithium-ion cell is about 2.8 volts. And this plateaus, it kind of looks like this. And when it gets to the discharge point, the output voltage decreases very steeply, and you don't really want to go on this point because you can damage the lifetime of the cell. So it's very important that you do not overcharge one. It's 4.2 volts in every spec I've seen, or plus or minus 50 millivolts. The lithium is kept in an ionized state, and if you overcharge it, you can get it in the solid state of lithium, and it's not a very nice element at all. That's why you see phones and skateboards and so forth catching on fire. So anyway, if we take a 4.2 Li-ion battery and connect it to a 741 and think about a V saturation voltage of plus or minus 2 volts, is we end up with a whopping signal swing here of about 0.2 of a volt. Not very useful. So let us introduce a CMOS operational amplifier, and a typical prefix on that is LMC, which stands for linear monolithic CMOS. And the output transistors in this are MOS transistors, and they don't have the voltage collector to emitter drop of a standard bipolar. And with the designs they have, they can come within millivolts of swinging to the supply rails. So here we see the output of a CMOS op-amp being fed from a fully charged Li-ion battery, and the peak-to-peak on this is nearly 4.2 volts. Now, of course, that depends upon the load, but that's a considerable improvement and basically enables low voltage audio without having high voltage supplies. Now, this particular part, this 6482, is guaranteed at 15 volts, which is surprising because some of these CMOS op-amps maximums like 5 or 6 volts, but this will actually work at 15. Its specifications are guaranteed at 15 volts, they're guaranteed at 5 volts, and they're guaranteed at 3 volts. So you've got a part here that can perform very well over a very, very wide supply ranges, and the input current biasing, since it's MOS, is very, very low. So that also helps. So that'll conclude, I think, with regard to single supplies. Yeah, it does. And this is kind of the future here, is low voltage. Many processors operate off 3.3, and some are sitting down at 1.8. So there's definitely a trend for low voltage, and the electronics today is truly marvelous. Using MOS transistors in analog applications was a thought that 15 years ago wasn't even on anybody's mind. So that concludes, and the whole purpose here is to make you aware of the single versus dual power supply issue, and also the low voltage issue, and some of the things that you have to do to provide a false ground, and let me say a clean false ground. So that'll conclude, and thank you for watching.